There's supposed to be an omega in the thumbnail, by the way. Does it look like an omega? My cameraman is going, woman. It's my partner. Camera woman. Shocker. So, angular velocity. That's what omega is. Omega represents angular velocity. And what it is effectively a way to express, I suppose, I don't want to say it's a way to express the distance travelled in a given time, because it isn't. It's a reflection of the angle that is subtended in a circular path within a given time frame, right? So if it's going really, really quickly and it has a high angular velocity, it's going to subtend a greater angle in a given time. That's what it is, okay? And we talk about it exclusively in circular motion. But yeah, why don't you check out my tutorial video, which is next, and it will explain this a little bit better. Alright, let's talk about angular velocity. Well, what is angular velocity? We've talked about what centripetal force is, and we've talked a bit about radians. So what is angular velocity? Okay, well, imagine a circular path, okay? An object is moving in a circular path, okay? So here it is. Here's my circle, and it's moving along like that, okay? Well, an object moving in a circular path will naturally move through an angle, and I've denoted that angle theta. So if it moves from here to here, it will have subtended an angle, okay? And it will have done that within a given time, okay? So the angular velocity, which is omega, okay, which is here, is used to describe the rate of change of this angle, okay? So effectively, the rate at which I subtend an angle in a circular path, or the rate at which I subtend this arc length effectively, is the angular velocity, okay, omega, which means that omega is equal to theta divided by time, the rate at which I subtend that angle, which makes perfect sense. And if we assume that time is equal to one time period, okay, then the object in question will move through that angle equal to 2 pi radians, because one time period is the time that it takes to complete one full rotation, right? And if we substitute that into our already known equation over here, we can say that omega, when t is equal to, well, when time is equal to period, I should say, omega is equal to 2 pi divided by big T, okay? And angular velocity is measured in radians per second, which is why we need to know and learn about radians. And additionally, given that frequency is the reciprocal of time period, whereby f is equal to 1 over t, we can also assume the equation omega is equal to 2 pi f, okay? All we've done is substitute this into here, okay, rearranged for t, and we can see that omega is 2 pi f. So these three equations, well, excuse me, here, you really need to know. Our 4 equations you really need to know. Okay, so let's see if we can take our knowledge and apply it to this question. An object takes 9.5 milliseconds to complete a single full revolution. Okay, that's a clue right there. And it says calculate the object's angular velocity in radians per second and in revolutions per second. Okay, well, what is revolution per second and how is it different from radians per second? Well, let's see if we can go through the working for this question, and maybe the answer will become a little bit clearer. Let me just clear that up. So we know that omega is equal to 2 pi over big T, where T is the time period. And the reason I'm using that equation is because I know that it's taken me 9.5 seconds to complete a single full revolution. Okay, so my time period is 9.5 milliseconds. As you can see here, I've converted that into seconds, and I've come up to an answer of 661.4 radians per second. Okay, totally fine. But it then asks me to convert my answer and to kind of show what that is in revolutions per second. And the revolutions per second is just the frequency, right? So it's kind of in the name. If there's a revolution, okay, we think of frequency as the number of times that something occurs in a given time period, right? So like if we have a wave, we have, you know, one oscillation, two oscillations, that's 2 hertz, right? That's our frequency. So it's 2 full oscillations in, let's say this is 1 second here, right? So frequency is effectively a measure of the number of revolutions that are occurring in a given second, right? So if we know that f is equal to 1 over t, we can just take our value for t and we can put it into here, right? Where it's 1 divided by t, and we get 105.3 revolutions per second. Okay, and that's because, as I said, frequency is a measure of the number of revolutions per second. Okay, and I've done a little footnote here for you to have a look at. Okay, that explains this in a little bit more detail. But this is effectively angular velocity, and those are the equations that you need to know here. Let's just get rid of this. Oh my goodness. Let's get rid of all this text. Yeah, these are the equations that you really need to be paying attention to. This one, this one, this one. Okay, you really need to know those when we're talking about angular velocity. In the meantime, here are some questions for you to try, so you can practice a bit more. And again, just take screenshots of this if you need it, save it. And then here are my workings for those questions. That's 1A and B, and this is 2A and B also. Okay, now that is the end of the tutorial on angular velocity. Alright, so hopefully you now have a better understanding of what angular velocity is. Yeah, this is like, you need to watch these videos in order, right? So we're going to plug them out to a week as usual, but don't watch video 8 on, you know, calculating vertical circles in circular motion unless you've watched this and stuff. Like, just don't, because it doesn't make sense, right? Watch them one at a time. So this is probably, you know, if you've not watched the radians video, this is like the cornerstone of the math that you need. But yeah, hopefully it was helpful. Please like and subscribe, please share, it really helps us grow the channel and get more quantum content to you guys. But in the meantime, stay quantum, and I'll see you soon. Bye!